This is team number 21083. We are representing our project, the Innovation Techniques in Wastewater Treatment Lab. So the overall scope or the overall goal of our project will be to design a wastewater treatment lab that's going to be located at the University of Arizona, the Chemical and Environmental Engineering Department specifically. The goal of the lab will be to use specific techniques, the classic techniques for wastewater treatment by purifying raw water that is mixed and modeled following the regional industry here in Southern Arizona. And the students will be able to mix up these techniques, use them in different orders. For our criteria and constraints for the criteria, we made sure that we are giving the students the best possible process by optimizing the safety, the cost, the separation measures. And for our criteria, we are using a pilot scale of 150 gallon per hour, also considering the space in Hashberger that everything is going to fit, and other conditions like the drain, temperature, etc.
This is our PNID for raw wastewater treatment lab. And as you can see here, we have three main components in our process: a coagulation flocculation unit, a set of ion exchangers, and two advanced oxidation process units here and here. Seen here, the raw wastewater will feed into a coagulation and flocculation unit to get rid of large particles, and then move into a filtration tower to get rid of any waste from the floc, and then splits into two streams. One being where an ion exchanger recycles ions back into the wastewater feed. The second being a stream that takes the filtered water into an oxidation process using ozone, peroxide, and UV light to degrade the organic.
The ideal floor plan for the process. On one side is the ion exchange, coagulation, flocculation, and ALP units. And on the other side is the RO membrane reactors. The top, right, and bottom of this floor plan shows a black dashed line, which depict open space. So if any equipment needed repairs, maintenance, or adjustments, this can be done from the outside.
It was important to the team and the department for this laboratory to reflect environmental factors specific to Arizona and its dominant industries. To achieve this and spark the thought of addressing environmental issues right here in our home state, 3 feed mixtures were created, each modeled after groundwater found in regions specializing in major industries of mining, agriculture, and industrial manufacturing involving metal runoff. The processes used in this laboratory differ slightly from those used currently to treat water from these regions in large scale, but create a potential to influence positive change in Arizona water treatment by demonstrating efficacy in these techniques on water with similar chemistry. Our 3 feed mixtures vary in turbidity from 30 to 17 and contain either the same contaminants as those found in nature, including silicates, organics, and metals. Coagulation captures colloidal particles governed by surface chemistry in the untreated water, using chemical reactions and electrostatic interaction to come together as floc. 2 classes of materials are removed by coagulation: turbidity and color. As the multivalent ionic coagulant degrades, colloids are destabilized in solution and floc begins to form within seconds of mixing. Therefore, the coagulant and the untreated water are first rapidly mixed to ensure exposure of all fine particles. This fluid is then sent to a flocculation basin and mixed at much lower RPM to encourage further interaction while allowing agglomeration and restabilization. In this animation, you can see the coagulant and feed mix quickly and intensely. In this first basin, the soluble charged particles are precipitated by the degradation of coagulant changing the ionic forces in the water. The contaminants precipitate out of solution, bind with the positively charged aluminum hydroxide ions, and are sent to the larger flocculation basin as shown, where the complexes, with now reduced repulsive forces, combine with each other due to van der Waals attraction to form a floc that is large, heavy, and dense enough to be separated from the clean water. Once floc is formed, common options for separation are sedimentation and decantation, flotation and sweep, and direct filtration. In this case, the latter was selected as a separation technique. Compared to conventional treatment, direct filtration has lowered capital and operational costs by using non-agitated tanks, reduced space by selecting a 12-inch diameter filter instead of a large basin, and lowered time requirements by foregoing an unrealistic 2-hour sedimentation and reducing the total residence time from 3 hours to 35 minutes. In addition, the amount and nature of sludge form is much more manageable and allows for complete treatment and recycle of the filtered out contaminants. Because the process fluid remains contained in equipment or hosing at all times, this method limits students' exposure to corrosive chemicals and sludge.
The ion exchange unit would be installed after the backwash of the coagulation unit. It is designed to remove the heavy metals such as aluminum so that this water from the backwashing of the coagulation unit can be reused in the raw water vessel. So we're not wasting so much water. So with the resin uses, the IRF 400 has been shown to selectively remove aluminum and to be replaced with sodium. And the ion exchange unit will be a dual regenerative tank system, meaning that while one side is exchanging the ions, the other side is regenerating, so this process doesn't come to a halt at the ion exchange unit, it can be continuous.
You might be asking yourself, what is an advanced oxidation process? Well, an advanced oxidation process, also known as an AOP, is a process in which hydroxyl radicals are formed which rapidly react and degrade with primarily organic compounds. There are many ways to form hydroxyl radicals, but the techniques that we'll be going over in our wastewater treatment lab are ozonation, peroxidation, and photolysis. As you can see here, these are two reactions that occur in our wastewater treatment lab. UV light can react with ozone in water to create hydroxyl radicals. It can also react with hydrogen peroxide to form these radicals as well. Ozone and hydrogen peroxide can also react on their own to form hydroxyl radicals. When these radicals react with organic compounds, they will produce minerals and salts. In this AOP experiment, we have two separate pieces of equipment that can create hydroxyl radicals. One being an ozone generator that is mixed in a tank with hydrogen peroxide at a constant concentration. In the top right, you can also see that lab bench ozone generator that would be used in this experiment. The dosage amount of ozone is adjustable from this, and that can change the ratio of the reactants. The other piece of equipment being a UV reactor, which radiates light at 254 nanometers with an adjustable power dosage in millijoules per centimeter squared. And that can vary up to 40 millijoules per centimeter squared to over 120 millijoules per centimeter squared.
The analysis conducted in this lab will combine practices commonly used in the field with more theoretical methods like modeling of kinetics. In week 1, students prepare to run the process by conducting jar tests to determine the optimal dosage of coagulant. We expect the results to look like the charts to the right. They will also calibrate metering pumps to deliver the desired flow rate at each pump location. In week 2, students will run the entire treatment plant and study the turbidity versus time data collected by the inline meters. They will also be asked to create a model for turbidity removal using techniques demonstrated by the graphs at the right, and compare this to the kinetics of polyaluminum chloride reaction with water proposed in literature.
And for our safety, we aimed for the minimum contact possible between the students and the chemicals. And we chose the best safer alternative for our contaminants. And we made sure that the chemicals are being stored, handled, and cleaned up correctly. Also, since we have the emission of silica and ozone, we are making sure that we are at low pressure or low temperature, making sure that nothing goes into students' skins or eyes, etc.
For future work and uncertainties, we still need to order the equipment, install and calibrate all sensors and pumps, as well as equipment, and then fully design a lab for students, meaning when they come to class and they see that they are up for this lab, that they know that they need to make a hypothesis, conclusion, and kind of give them those steps towards doing this lab. Still, we're uncertain of how the theoretical values will relate to the experimental values, meaning, in theory, that this water should be reused and recycled, but only the experimental values will really show if we can do this, or that we need to have this waste need further treatment. The U of A only allows a certain amount of chemicals to go down the drain in certain concentrations. So we have to meet that requirement, or we have to send that to somewhere else to have them treat the water.